Good morning. Assalamualaikum. My name is Anika Malia from Group 4. Today we are presenting our project on preemptive scheduling, STR, and round robin. Here our team members are Ryan, Abrar, Rojitra, and myself. First, what is CPU scheduling? It's an OS function that decides which progress or process gets the CPU, when, and for how long. Think of a bank with a teller and many customers. The teller is the CPU, and the customers are the processes, and manager is the scheduler. Why it is important? Keeps CPU busy, reduces waiting time, ensures fairness, makes system responsive. Here is another term which is like primitive versus non-primitive. Primitive is OS can interrupt a running process. Non-primitive is process runs until it finishes. We are focusing on primitive schedule today. Our project compares with two algorithms: shorten remaining time, which is SRT, prints the shortest job first, like an officer printer, efficient and short job finish fast. Another thing is long job may starve, and secondly is the round robin RR, and it gives everyone a fixed time limit, rotates equally, and it's fair, no one starves, and higher waiting time and overhead. This is all, but in short, SRT is efficient but unfair, and RR is fair but slower. Now I'll pass it to my teammate.
Okay, Assalamu alaikum. I am Rayan Bahaddin and I will continue with real world scenario. Okay, we have printer sharing in an office scenario. We have three employees which are representing the number of processes, and we have pages to print which are representing the burst time. Process 1 has 5 pages to be printed, process 2 has 3 pages, and process 3 has 4 pages. In SRT or SRTF algorithm, it will pick the processes based on the minimum burst time, and in this situation, the minimum number of pages. So here, the minimum one is process 2. So it will take process 2 first, followed by process 3, and lastly process 1. Process 2, then process 3, and lastly process 1. SRT keeps the printer efficient by always printing the shortest job left first, but a large document such as process 1 risks getting delayed indefinitely if smaller print jobs keep arriving ahead of it. The same situation, but in round robin algorithm. Round robin algorithm will choose the processes one by one based on a fixed amount of time, which is called quantum time. In this situation, the quantum time is equals to 3. So it will start with process 1 and print 3 pages out of 5 pages. So the remaining is 2 pages. Then it will move to process 2, and same it will print 3 pages. So process 2 is already done. After that, it will move to process 3 and print 3 pages out of 4. So the remaining is 1 page. After that, it will return to process 1 and printing the remaining, which are 2 pages. And after that, it will go to process 3 as process 2 is already done, and then it will pay the remaining 1 page for process 3. So everyone gets a fair turn, and that is exactly what round robin does with the CPU time instead of pages.
Good day, doctor. My name is Rujitra, and I will be presenting the implementation of shortest remaining time SRT scheduling algorithm. For this project, I developed the simulation using HTML, CSS, and JavaScript. So this is the simulation. So to test the algorithm, I will use 4 processes with different arrival times and burst time. So the first arrival time is 0, burst time is 8. Second process, the arrival time is 1, burst time is 4. Third process is arrival time is 3. Burst time is 9. The last process arrival time is 4. Burst time is 5. So now I will start the simulation. Average waiting time is 6 and the average turnaround time is 12.5. So initially, P1 starts executing because it is the first process in the ready queue. When process P2 comes in at arrival time of 1, it has a remaining burst time shorter than P1. So the CPU pregames the P1 and started executing P2. When P3 arrives at arrival time 3, the burst time is longer than P2's remaining time, so P2 will still continue to run. The same happens with P4 arrives at time 3 because P2 has the shortest remaining time. After P2 finishes, the algorithm compares the remaining times of P1, P3, and P4. Since P4 has the shortest remaining time, it executes next, following by P1 and P3. Once all the processes have completed, the simulation automatically calculates the waiting time, turnaround time for each processes and display the results all together along with the Gantt chart. So this is the Gantt chart and this is the result of each processes. So this demonstrates that how SRT algorithm always prioritizes the process with the shortest burst time to improve scheduling efficiency. Thank you.
Hello everyone, my name is Abrar and today I'll be presenting my part for CPU scheduling simulator, specifically for the round-robin primitive algorithm, which how it functions is that it works as all the processes get equal time slices by the equal time slices from the CPU until the next process is executed, until the next process starts its execution. The process execute in order of their arrival, and if the process do not complete its burst time during the allocated time, then it will be sent back to the rear of the queue. So in this simulation of ours, if I have process 1 and its burst time is 8, process 2, its arrival is at 2 seconds and burst time is 4, process 3 arrives at 3 seconds and its burst time is 5, and finally our process 4, it arrives at 4 seconds and its burst time is 3, for instance. So I have all of my processes along with their arrival time and burst time. So if I start the simulation, I get a Gantt chart that shows to me how the CPU would allocate each and every process and allocated each and every process, along with the processes statistic, which shows us the processes, each processes, their arrival time, their burst time, their completion time, which can be calculated by the arrival time minus the duration it took for them to reach their destination. So in P1's case is 21, and you continue calculating like that. The turnaround time, which is how long, which is burst time minus completion, which is completion time minus burst in order to get this. And then the waiting time, which is turnaround minus completion, which we get 12. Along with it, we can find the average waiting time, which for this simulation is 10.25, and the average turnaround time, which is 15.25, which is calculated by the total of turnaround divided by number of processes, which is 4. And same thing with the waiting time, addition of all of the values from processes divided by the number of processes, we get our average waiting time. And that's all for me.